Today we're going to talk about counting outcomes and theoretical probability. So counting outcomes and theoretical probability.
This sounds like really confusing stuff.
It sounds really confusing, but it'll make a lot more sense once you see what it's actually talking about. It's just,
It's a fancy name for something really easy.
it's a fancy name for something that's pretty.
Can it just be a fancy name for adding like small numbers?
It'd be a fancy name for like a really easy addition like one
Just like
We are going to do some very simple counting. So
like
there's
1,
that.
2, 3, 4, like that's it.
Dakota, please don't bang your desk. Prob is an abbreviation for probability because it does not fit. So go on and turn to page 36 for Unit 5 objectives. Yeah, Unit 6, my bad. So page 36, Unit 6 objectives. So yesterday we talked about writing percents as fractions and decimals, and writing decimals and fractions as percents. Today we're going to talk about using a tree diagram and the counting principle to count possible choices. Use a tree diagram and the counting principle to count the possible choices. And we're also going to find theoretical probability by counting outcomes. So flip on over to page 40 once you've got that written. Dakota, page 40, please. So page 40. We still need that, someone? So page 40 at the top, go ahead and write counting outcomes and theoretical probability on page 40. So counting outcomes and theoretical probability. So the first thing that we're going to talk about today is something called the counting principle. And the counting principle states that if there are m choices for one thing and n choices for another, then there are n times m choices for that item. It'll make a lot more sense once we do a problem. Okay, so the definition of counting principle if there are m choices for one and n choices of another, there are m times n choices. I don't know. So let's take a look at an example of what this looks like so it makes a little bit more sense. So we're going to work through a problem, and the problem is Hawker Grove is selling t-shirts. Hawker Grove is selling shirts. There are two color options. We're going to go with black and red since those are our school colors. Two colors, black and red. Two colors, black and red. They're offered in men's and women's cuts. As well as short and long sleeved. So we have Hawker Grove selling shirts. There are two colors, black and red, offered in men's and women's, short and long sleeve. So the question is, how many shirt options are there? That's the counting principle. So the way we're going to solve this out, and we're going to work through this, is we're going to make what's called a tree diagram. That's fine.
Does it look like a tree?
It looks like branches.
Can we color these?
You can write it in green if you like, but
Can we make blue leaves?
no.
Wait, is this that kind of thing that's like how many options are there for like this and that?
Yes. Okay. So how we're going to do this is we're going to do a tree diagram. For sake of space, we're going to use R for red, B for black, M for men's, W for women's, L for long, S for short. So the types of shirts that we have. So we have a red shirt and a black shirt. Those are our first two options from our problem, correct?
Yeah.
So we have two options off of that, men's and women's, right? So we have men's and women's for both red and black shirts.
Oh, this.
It can be a pyramid. It's technically called a tree. You can call it whatever you like, but this is what it's called.
Call it.
And for men's and women's shirts, there's long sleeved and short sleeved. So we're going to have long sleeve shirts and short sleeve shirts for each men and women's in red and black.
Is there gonna be a faster way to do this than drawing?
This is just going to show you. Hmm?
There.
Yes. Declan, please face forward. Declan, sorry. Audrey and Christy. Okay, so now across the bottom, how many options of shirts do we have? We have 8. So we have 8 options of shirts. Dakota, please face forward. Okay, so referring back to our counting principle definition, if there are M choices for one and N choices for another, there's M times N choices. So in this case, we had 2 choices for black or red, or 2 choices for colors, 2 choices for men's or women's, and 2 choices for short and long. So M times N, or 2 times 2 times 2 equals 8. So we have color times male or female times length. So color times sex times length is 2 times 2 times 2, which equals 8. So that's the counting principle. If you don't want to make this tree, unless it tells you to make the tree, you don't have to. There are some problems on your homework it tells you you have to make the tree. It's practice. It's just something we need to work on. But the counting principle states that you can multiply the options, and that's how many total options you'll have. So there are 8 options, 2 times 2 times 2, or the branch it out, we had 8 options. Is everybody seeing that?
Yeah.
Tommy? So now that we have that, let's talk about theoretical probability, that big word. So theoretical probability. So when you see theoretical probability, it might be in your book in this notation of the probability, or P, of an event. So we have the theoretical probability, or P, of an event. So when we see this, we're going to make a fraction or a ratio. And on the numerator, we're going to have number of favorable outcomes. So on top, we're going to have number of favorable. So number of options that the problem is asking if it will happen or not. And what do you think we're going to put on the bottom, the denominator? So on the numerator, we have the number of favorable options, Triana. The number of total options. So on the denominator, we're going to put number of total, or number of possible outcomes. It'll make sense in a second. Tommy, we can address that after the notes, all right? So, theoretical probabilities, the probability event. The numerator is the number of favorable events over the number of possible events. So let's look at something a little more concrete instead of a little something less abstract, all right? So let's say, what's the probability of tossing a coin, or tossing two coins, and both of them are tails? Let's go work through it so we can show how this works. What's the probability of tossing a coin and both are tails? So let's write this.
Two coins and both
Well, we're gonna work through it. All right.
1, 2, 3, 4. So 2 out of 4, right? No.
What age?
Let's work through it so we can see what it looks like. Tommy, place forward, please.
5, 6.
We'll work through it, Reagan.
All right.
What is the possibility or probability So we're going to make another tree diagram or line, pyramid diagram, whatever you guys wanted to decide to call it. It's an upside down tree.
It looks like a tree.
Go.
Like upside down.
It could be the roots of the tree or it's an upside down tree, whatever you prefer. So the first time we have two options of heads and tails, right? When you're flipping a cone, you have two options of heads and tails, correct? That's highly unlikely.
Yes. But it's still possible.
So you flip a coin, it's heads or tails. Bless you. You flip that heads, and then it has two options again. It could be heads, or it could be tails. Right?
What's the age for?
Heads and tails.
No, like the first age. Both of them are for heads.
You flip the coin the first time, you get heads. You flip the coin the second time, you can get heads or tails, right?
So the first, so the top H is for the first flip.
The top H is for the first flip.
Bottom two are for the second.
The bottom two are the second flip. Good, Haley. Dakota, face forward, please. So you flip the coin and you say you get tails. You have two options after that. You can get heads or you can get tails, right? And we're looking to see both are tails, right? So the first time you got heads. So you can't have two tails, right? So the second time you got tails, and then you got tails one here time. So we got two tails. So across the bottom, how many options did we have? We had 4 total options. We had 4 total options. How many were favorable? 1. So number of favorable options that we had.
So it'd be 1 over 4?
We had 1 favorable option. We got tails twice, 1 time. And the total number of options that we had?
4.
4.
Dude, I totally guessed this.
Oh my gosh, I feel so smart right now.
Does that make sense? Is that a question, Dakota? Triana? Ladies and gentlemen, I can't hear Triana's question because we're talking. Yeah, so the question asked, what are the probability that you flip a coin twice and both are tails? So the first time we got heads, say we got heads. The second time we flipped it, we got heads and tails. But if we got tails the first time and we flipped it again, we got heads and tails. Those are your two options. So here, 2 tails, that's the probability. That only happened once. And we had 4 total options. So the bottom, we had 4 possible outcomes, and we only had 1 favorable outcome from the question that was asked. Does that make sense? Did that clear it up a little bit better? Go to face forward, please. So now we're going to talk about another theoretical probability question involving winning the lottery. So it says, what are the chances of winning the lottery where the ticket has 6 numbers on it and you buy 4 tickets? What is the probability that you have the winning ticket? Let's work through it. Yeah, it's going to be 1 out of a lot. Let's work through it, all right?
1 out of a million.
We can work through it and we can find the answer.
Let's do it then.
So what are the chances of winning the lottery where the winning ticket has 6 numbers on it and you purchased 4 tickets? What is the probability you have the winning ticket? We'll work through it and we can find the answer. Dakota, face forward, please. Okay, so there's 6 digits, 6 numbers on this winning lottery ticket. So that means there's how many different options for the first number?
6.
How many numbers are there?
4.
Digits, just 0 through 9.
Oh, 9.
0 through 9.
Oh, 10.
10. So for the first ticket, or for the first digit, there's 10 options. And the second?
10.
10. And so on. So how many? We have third option, 10, fourth, 10, fifth, 10, and sixth. So what's 10 times 10 times 10 times 10 times 10 times 10? Put it in your calculator. It's a really big number. It's 1 million. How'd you get there so fast? So there's 6 zeros, right?
So you add 6 zeros.
Yeah, so there's 1 million options. So 1 million total possible outcomes.
It's a million.
So we have 1 million possible outcomes, and how many tickets did we buy?
6. 4.
We bought 4 tickets. So there's 4 favorable outcomes out of the 1 million options that we got.
Wow.
And it's much, much worse in real life. This is just a very sample, small
Is it
size.
like in real life? It's like 1 in like 7 billion.
It's a lot worse than that. What was that, Declan? Or Declan?
According to our data, it's 1 in 250,000.
And how did you find that?
Because I divided 1 million by 4.
So you divided 1 million by 4. So that gave us 250,000. So there's a 1 in 250,000 chance that this small sample problem you got to the winning lottery ticket.
That's too much. I'm not.
Don't play the lottery then.
Do you?
No. Because the chances are much worse than that.
Well, let's find out, shall we?
Tyson, close your computer. Close the computer, please.
At least by 5. We have to split the money
No.
if we win.
Okay, so does that make sense how we work through that?
Yes.
We have 1 million total options because there was 10 digits for each place in the number. Haley?
Since we got 4 in 1 million, and like that's not simplified simplify, do we have to like simplify it to like 1 or 2 or 3?
Yes, you have to simplify it.